Hello and welcome to the 6th video in this series on trigonometry. Now in this video I would like to just talk about some special values that the sine, cosine and tangent functions have for particular angles. And these are very helpful to know if you're doing trigonometry for some simple cases. Let's just go back and remind ourselves quickly of some definitions. So here's a right angle triangle. Let's call this vertex A, C, B, lengths A, B, C. C is the hypotenuse. And we define sine of A to be the opposite over the hypotenuse, the cosine of A to be the adjacent over the hypotenuse, and the tangent of A is the opposite over the adjacent. We also know the tangent of A can just be written as the sine of A divided by the cosine of A. And we also showed that the square of the sine plus the square of the cosine is equal to 1. So that's just a very quick recap. Now let's think, if we make this triangle very, very flat, okay? So let me draw an extremely flat right angle triangle there. So I have a tiny little angle A. Do you see that the sine of A is going to be a very small number because it's the opposite length over the hypotenuse? So as the angle A goes to 0, what we can expect is that the sine of A will go to 0 as well, because this opposite length will just vanish as the angle A vanishes. At the same time, the cosine of A, which is the adjacent over the hypotenuse, these two lengths become essentially equal. It's like a hairpin. And so the cosine of A should approach 1. And you see how that's consistent with this little formula here, because the square of the sine plus the square of the cosine must always add to 1. So if sine starts to go down to 0, then cosine must approach 1, because the sum of the squares has to equal 1. Similarly, if I draw a very tall right angle triangle like this, and that's angle A now, this is the right angle. Do you see now that as the angle A approaches the biggest it can be, which is 90 degrees, at least in this right angle triangle, as that angle vanishes up there, then now it's the cosine which is going to shrink to 0, because this length is going to get smaller and smaller and smaller as A approaches 90 degrees. So cosine of A will approach 0 as A approaches 90 degrees, and the sine of A will approach 1, because the opposite length will become very, very similar to the hypotenuse. So if we make a table of special values, we already have a good sense of what's going to happen. Make sure I can fit this in. What's going to happen as the angle goes to either 0 or 1. So if you just bear with me for a second while I just get this table ready here. Okay, that should be fine, I think. So the angles I want to look at are 0 degrees and 90 degrees. I want to ask about the sine of A, the cosine of A, and the tangent of A. And I'm also going to look at some special angles. There are 3 angles between 0 and 90 where some simplification happens. These are 30 degrees, 45 degrees, and 60 degrees. And what we've already seen is, from just sort of common sense, drawing very skinny or very sort of peaked triangles, is that when a is 0 degrees, the sine of a will be 0, cosine of a will be 1, and then at 90 degrees, the sine of a will be 1 and the cosine of a will be 0. The tangent of a we can always just get from the ratio. So 0 divided by 1 is 0, so the tangent of a will be 0 at 0 degrees. At 90 degrees, the poor old tangent becomes undefined. So let me, in quotation marks, just put infinity here, and we'll be a bit more precise about this when we start to draw the functions of sine, cos and tan, and we'll see much more clearly what happens to tangent around 90 degrees. But for our purposes here, it goes to infinity as the angle A approaches 90 degrees, because you're dividing a number very close to 1 by a number very close to 0. Okay, now the rest of these values you can either try to memorize, or you can have some special little triangles which motivate the values. Let me give you these special triangles. These can be harder to remember than just remembering the values themselves, actually. So it sort of depends whether you're a sort of a visual person or whether you're sort of a numbers person. If you're a visual person, you'll like these little triangles because they help you get the values. Let's imagine we have a right angle triangle whose sides are 1. And then let us use Pythagoras' theorem to work out the hypotenuse. We have 1 squared plus 1 squared is 2, and so the square of the hypotenuse is 2, so the length of the hypotenuse is the square root of 2. Because it's an isosceles triangle, these two angles are the same. They have to add up to 90 degrees, so be 45 degrees. And so we can read off very quickly in this table what happens. The sine of 45 is the opposite over the hypotenuse. That will be 1 divided by root 2. The cosine of 45 will be the adjacent over the hypotenuse, also 1 over the square root of 2. The tangent will be the opposite over the adjacent, which is 1, and that's confirmed by just looking at the tangent as the sine over the cosine. We have the same number divided by itself, which gives 1. These results are also consistent with this formula. If I square 1 over root 2, I get, let's just check this, 1 over root 2 squared is 1 over root 2 times root 2, which is just 1/2. And so you see the square of sine here is 1/2, and so the square of cosine will be 1/2, and those squares add to 1. So that's all consistent. The other triangle that you can try to remember is this one. It's an equilateral triangle of length 2, where each angle is 60 degrees. So an equilateral triangle. And if you bring down a perpendicular bisector here, you make a right angle triangle. This length now is 1, and this angle is 60, and because we bisected, this angle here is 30. And you can use Pythagoras in reverse here to get this length. So this length here, let's call it b. We'll have that b squared plus this length squared, which is 1 squared, will equal the hypotenuse squared, which is 2 squared. So b squared will be 2 squared, which is 4, minus 1 squared. So b squared will be 3, and so b will be the square root of 3. And then we can read off our values here. So if I look at 30 degrees, for example, sine of 30 will be the opposite over the hypotenuse, which will be 1 over 2. So sine of 30 is 1 over 2. Cosine of 30 will be the adjacent over the hypotenuse, is root 3 over 2. And at 60 degrees, the sine of 60 will be opposite over the hypotenuse, root 3 over 2. And the cosine of 60 will be the adjacent over the hypotenuse, which is 1 over 2. Do you notice how there is a diagonal symmetry between sine and cosine? And that's because these two angles have to add up to 90 degrees. So when we talk about the sine of A being this over this, the sine of A being this over this, we may as well be talking about the cosine of B being this over this. So that's why we have this diagonal symmetry between 0 and 90 degrees. And so if you know sine 30, you automatically know cos 60, and if you know cos 30, you automatically know sine 60, and so on and so forth. And in fact, it's that symmetry that says that sine and cosine have to be the same at 45 degrees. Right, so those are those values, and then the tangent we can either read off from the triangle, or for practice we can read off from the ratio. So the tangent is sine over cosine, so this divided by this would be 1 divided by root 3, and for 60 degrees the tangent will be sine over cosine, this divided by this is root 3. I'm sort of doing it quite quickly, but you'll be very able to check these by doing your division of fractions and just checking that these values are correct. So those are the special values. In fact, you know, if you can just remember that sine of 30 is a half, you can get everything else in this table pretty much, either using symmetry and using these relationships for tan, and also between sine and cos. Remember when I said that if you know the sine of an angle, you can work out the cosine, and if you know sine and cosine, you can work out the tangent. So if you know the top row of this table, you can work out all the rest, and you can even sort of infer the top row from symmetry. The only one that you sort of need to remember is that sine of 30 is a half. Alternatively, these triangles sort of give you all the information, but actually I personally find these harder to remember and reconstruct than just some key information here and reconstructing the rest by symmetry and using these relations. So these are the special angles between 0 and 90, for which sine, cos and tan have relatively simple values, and if you can commit those to memory, that would be very helpful. I think examiners, certainly in the Scottish curriculum, expect students to commit these values to memory. So thank you very much for your attention. In the next tutorial, we're going to look at sine, cos and tan as functions and see how they appear on a graph. So I'll see you then.